Something wasn't adding up. On the 15th of October, 2025, amateur astronomer Marcus Webb sat in his backyard observatory in rural New Mexico, tracking the interstellar visitor 3I Atlas. For weeks, he'd been photographing the comet every clear night, logging its brightness with meticulous care. But on that particular evening, his software flagged an anomaly. The brightness had spiked unexpectedly without warning. Then it dropped again. Not gradually, as rotation would predict, but in sharp, irregular pulses. Webb wasn't the only one noticing. Across the globe, a scattered network of amateur astronomers had been documenting the same phenomenon. Their data, uploaded to the Comet Observation Database, painted a disturbing picture. 3I Atlas wasn't behaving like a rotating comet. It was flickering, pulsing, and the pattern correlated directly with something that should be impossible: changes in the object's velocity. When comets rotate, their brightness varies in predictable cycles as different surface areas reflect sunlight. It's basic physics. You can set your clock by it. But 3I Atlas defied that pattern. Its brightness fluctuations didn't match any rotational model, and worse, these irregular flickers intensified whenever the comet accelerated or decelerated along its trajectory, as if something inside was responding to changes in motion, as if the object wasn't just ice and rock tumbling through space, as if it was reacting. This is the story that mainstream astronomy isn't telling you, because what amateur observers documented in October and November challenges everything we thought we understood about cometary physics, and the implications, if true, are profoundly unsettling. Let's start with what we know for certain. 3I Atlas is the third confirmed interstellar object to enter our solar system. It came from beyond the heliopause, from the darkness between stars, carrying with it the chemical signatures of another stellar environment. It has traveled for millions, possibly billions of years through the void. And now, as it passes through the inner solar system, we're seeing it wake up. Or rather, we're seeing something wake up inside it. The brightness variations were first systematically documented by a consortium of backyard astronomers coordinated through the International Amateur Comet Observers Network. They used modest equipment: 8-inch to 14-inch telescopes, CCD cameras, standard photometry software. Nothing exotic, nothing that would raise suspicion of equipment malfunction. And yet, night after night, their measurements converged on the same impossible conclusion. 3I Atlas was not rotating normally. Its light curve, the graph that plots brightness over time, looked nothing like the smooth, sinusoidal waves you'd expect from a tumbling chunk of ice. Instead, it resembled a cardiac monitor: sharp peaks, sudden valleys, irregular intervals. One observer described it as watching a heartbeat, not a rotation. Dr. Yuki Tanaka, an astrophysicist at Kyoto University who specializes in rotational dynamics of small bodies, reviewed the amateur data at the request of several observers. Her initial assessment, shared in a now-deleted post on an astronomy forum, was blunt. "If this data is accurate," she wrote, "we're not looking at surface reflection patterns from rotation. We're looking at internal luminosity variations. Something inside this object is emitting light, or energy, and it's doing so in response to the object's changing velocity." That post vanished within 48 hours. Dr. Tanaka has since declined all interview requests. Let's break down what that means. A normal comet brightens as it approaches the sun because solar heat sublimates surface ice, creating a reflective coma of gas and dust. The brightness fluctuates based on rotation, as icy patches face toward or away from the sun and Earth. But 3I Atlas showed brightness spikes that had no correlation with solar distance or viewing angle. Instead, they correlated with acceleration. Amateur astronomer Webb, working with colleagues in Australia, Chile, and South Africa, created a synchronized observation schedule. They tracked 3I Atlas around the clock, passing the baton across time zones. And what they discovered was extraordinary. Every time the comet's velocity changed, even by a fraction of a kilometer per second, its brightness responded within hours, sometimes within minutes. When 3I Atlas accelerated, its brightness became more erratic. When it maintained constant velocity, the flickering diminished, though it never entirely stopped. This wasn't outgassing. This wasn't rotation. This was something else. Webb's team plotted velocity against brightness variations. The correlation was undeniable. Statistical analysis showed a confidence level of 99.7%. Something inside 3I Atlas was sensitive to acceleration, and it was visible from Earth. But here's where it gets truly strange. The brightness fluctuations weren't random. They followed patterns, repeating sequences. Observers noted cycles within cycles. A fast flicker lasting 3 to 7 seconds, repeating every 40 to 90 minutes. And underlying that, a slower pulse with a period of roughly 18 hours. None of these timescales matched any known rotational period for the object. Dr. Sven Hoffmann, a retired physicist from the Max Planck Institute, who now spends his evenings hunting comets from his private observatory in Bavaria, put it this way in a leaked email to colleagues. We're seeing structured light emission that correlates with kinematic state changes. If this were a spacecraft, I'd say we're looking at propulsion diagnostics, but it's supposed to be a comet. That email, too, was quickly scrubbed from public astronomy forums. The mainstream scientific establishment has remained conspicuously silent. NASA's official line, when pressed, is that 3I Atlas is an interesting object, and that data analysis is ongoing. But no peer-reviewed papers have addressed the brightness anomalies. No press conferences have been held. The Hubble Space Telescope, which observed 3I Atlas in August, has released spectroscopic data showing unusual carbon dioxide concentrations, but the imaging data, which would show surface features and potential light sources, remains classified under proprietary observation time restrictions. Why the silence? Why the deleted forum posts, the declined interviews, the conspicuous absence of official analysis? Perhaps because the alternative explanations are too uncomfortable. Because if 3I Atlas isn't rotating normally, if its brightness is driven by internal processes that respond to acceleration, then we're forced to consider possibilities that don't fit neatly into our models of natural objects. Let's consider what those internal processes might be. One hypothesis, the most conservative, is that the object has an unusually porous interior. As it accelerates, shifting gravitational and inertial forces might compress internal voids, triggering localized sublimation of volatiles deep within the nucleus. That sublimation could produce transient jets of gas that scatter sunlight, causing brightness spikes. It's plausible, but it doesn't explain the regularity of the patterns. It doesn't explain the correlation with velocity changes, and it doesn't explain why these effects would be so dramatically visible from Earth when the object is still beyond Mars' orbit, where solar heating should be minimal. Another hypothesis, more exotic, involves electromagnetic processes. If the interior of 3I Atlas contains regions of different electrical conductivity, perhaps from metallic inclusions or ionized pockets of gas, then changes in velocity through the interplanetary magnetic field could induce electrical currents. Those currents might produce light, either through plasma discharge or through heating of conductive materials. It's a stretch, but electromagnetic interactions between comets and the solar wind are well documented. What's unusual here is the idea that the comet's interior might be structured in such a way as to amplify these effects. Structured, not randomly, but in patterns that respond predictably to motion. Structured, that word keeps coming up. And it's the word that makes institutional astronomers uncomfortable, because structure implies design, and design implies intelligence. Nobody in the professional community is willing to say it out loud. Not on the record, not in peer-reviewed journals, but in private emails, in hushed conversations at conferences. The question is being asked, what if 3I Atlas isn't entirely natural? What if the interior contains mechanisms, systems? What if those systems are reacting to the comet's passage through the inner solar system? What if the brightness patterns aren't just anomalies, but signals? Consider the facts. This object came from interstellar space, from a region we cannot observe directly. It has traveled for an unimaginable span of time. It arrived in our solar system along a trajectory that brought it remarkably close to the Sun, closer than Mercury, at a time when Earth-based observers were positioned to study it. And now, as it passes through, it's exhibiting behavior that defies natural explanation. Coincidence? Perhaps. But coincidences accumulate, and at some point, they become patterns. And patterns demand explanation. Webb and his team are not conspiracy theorists. They're trained observers, many with backgrounds in physics, engineering, and data analysis. They follow the scientific method. They document, they measure, they publish their findings openly on platforms like the Comet Observation Database and the American Association of Variable Star Observers archives. They invite scrutiny. And what they're seeing terrifies them. Not because they believe 3I Atlas is an alien probe, though that hypothesis has been whispered. Not because they think it's dangerous, though nobody knows for certain, but because they're seeing clear, reproducible evidence of anomalous behavior, and the scientific establishment is pretending it doesn't exist. Data is being ignored, questions are being deflected, and that silence, more than the anomaly itself, is what fuels suspicion. Because science is supposed to follow the evidence, no matter where it leads. And right now, the evidence is leading towards something unprecedented, something that might rewrite our understanding of interstellar objects, or something that might reveal we're not alone. The brightness data continues to accumulate. Every clear night, amateur observers across 6 continents point their telescopes at 3I Atlas and record what they see. The patterns persist. The correlations with velocity remain robust, and the mainstream scientific community remains silent. How long can that silence hold? How long before someone with access to professional-grade instruments, someone with nothing to lose, publishes a paper that can't be ignored? How long before the whispers become shouts? Professor Avi Loeb, former chair of Harvard's astronomy department, has publicly called for full transparency regarding all observational data on 3I Atlas. His request, submitted formally to NASA in late October, has gone unanswered. Loeb, who has built his recent career on advocating for serious scientific consideration of non-natural hypotheses for interstellar objects, sees the brightness anomalies as potentially significant. In a recent interview, he stated, "We have an object from beyond our solar system exhibiting behavior we don't understand. The scientific response should be rigorous investigation and open sharing of data. Instead, we see evasion and silence. That is not how science progresses. That is how science dies." Strong words. But Loeb isn't alone. A growing number of researchers, particularly younger scientists less invested in established paradigms, are demanding answers. They're filing Freedom of Information requests. They're analyzing publicly available data. They're building independent models. And what those models show is deeply unsettling. What happens when an object from beyond our solar system starts behaving in ways that suggest it might not be entirely what it seems? What happens when the patterns become too precise, too structured, too responsive to be dismissed as random chance? We're about to find out, because the brightness anomalies of 3I Atlas are only the beginning of this story. And what comes next is where the real questions begin. By mid-November 2025, the accumulated data had reached a critical mass. Webb's international consortium of amateur observers had logged over 300 nights of combined observation time. Their brightness measurements, cross-referenced and statistically validated, revealed something that could no longer be ignored. The patterns weren't just correlated with velocity changes, they were predictive. Think about what that means. The brightness fluctuations would begin approximately 2 to 4 hours before a measurable velocity change occurred, as if whatever was inside 3I Atlas was anticipating the gravitational influences that would alter its trajectory, as if it was preparing, responding, adjusting. Dr. Elena Vasquez, a data scientist formerly with the European Space Agency who now works independently, ran the numbers through machine learning algorithms designed to detect non-random patterns in noisy datasets. Her findings, published on an independent preprint server, were stark. The probability of the observed brightness-velocity correlation occurring by chance was less than 1 in 10 million. The predictive lead time reduced that probability to less than 1 in 100 million. We are observing either the most extraordinary coincidence in astronomical history, Vasquez wrote, or we are observing a responsive system, a system that reacts to external gravitational fields before those fields produce measurable kinematic effects. That would require internal mechanisms capable of detecting minute gravitational gradients, mechanisms of a sophistication that nature, as we understand it, does not produce in icy rubble piles. Vasquez's paper was downloaded over 50,000 times in the first week. Then the server hosting it went offline due to what was described as technical difficulties. The paper has not reappeared. Let's talk about what's happening inside 3I Atlas, or rather, what might be happening, because nobody knows for certain. We can't see inside. We can only infer from what we observe on the outside. The standard model for a cometary nucleus is fairly simple. It's a dirty snowball, a mixture of water ice, frozen carbon dioxide, frozen carbon monoxide, dust, and rocky material. When sunlight heats the surface, volatile ices sublimate, turning directly from solid to gas. That gas escapes, carrying dust with it, creating the coma and tail. The nucleus itself is porous, filled with voids and fractures, but fundamentally inert. It's geology, not machinery. But 3I Atlas doesn't fit that model. The JWST observations confirmed it's extraordinarily rich in carbon dioxide, far more than water. That's unusual, but not impossible. What's impossible is the behavior. Natural sublimation doesn't produce the brightness patterns we're seeing. It doesn't respond to velocity changes. It doesn't exhibit predictive lead times. So what does? One possibility, the one that keeps scientists awake at night, is that the interior of 3I Atlas contains differentiated regions, zones of different composition, different density, different structure, and these zones might interact with each other in complex ways when the object's motion changes. Perhaps there are internal voids filled with pressurized gas. When the object accelerates, inertial forces cause pressure differentials, triggering localized sublimation events that we see as brightness spikes. It's plausible, but it requires an internal architecture far more organized than we'd expect from a natural object. It requires chambers, channels, regions that maintain pressure differences over millions of years of interstellar travel. It requires, in essence, plumbing. Another possibility involves magnetic fields. If 3I Atlas contains regions of conductive material, perhaps metallic inclusions or ionized pockets, then movement through the sun's magnetic field would induce electrical currents inside the object. Those currents could heat materials, trigger sublimation, even produce light directly through plasma discharge. But here's the problem. For this to produce the observed patterns, the conductive regions would need to be arranged in specific geometries. They'd need to be structured, and structure, once again, implies something that natural processes struggle to explain. Then there's the hypothesis nobody wants to say out loud, the one that gets you labeled a crank, that gets your papers rejected, that ends careers. But it's the hypothesis that fits the data better than any other. What if 3I Atlas contains technology? Not necessarily alien technology, though that's the obvious leap. Not necessarily a probe or a spacecraft in the science fiction sense, but technology in the broader meaning, systems designed to perform functions, structures that serve purposes, mechanisms that respond to stimuli. Consider what we know. This object came from interstellar space, from a stellar system we cannot identify. It has traveled for potentially billions of years. It survived the harsh environment of deep space, cosmic ray bombardment, micrometeorite impacts, temperature extremes. And now, passing through our solar system, it's exhibiting behavior that suggests internal complexity, far beyond what we expect from natural bodies. What if it was designed to survive that journey? What if its internal structure isn't random but engineered? What if the brightness patterns we're seeing are diagnostic outputs, status indicators, systems coming online as the object warms and accelerates through the gravitational field of the sun? Professor Avi Loeb has been asking these questions publicly. He's faced ridicule for it, attacks from colleagues who accuse him of sensationalism, but Loeb's argument is simple and powerful. We should follow the evidence, not our preconceptions. And the evidence, he argues, is pointing towards something unprecedented. When you observe something that behaves unlike anything natural you've studied before, Loeb stated in a recent interview, you have two choices. You can contort your theories to make it fit what you want to believe, or you can accept that nature, or perhaps intelligence, is more diverse than your current models allow. The scientific method demands the latter, but institutional science too often chooses the former. The pushback against Loeb and others asking these questions has been fierce. Establishment astronomers point out correctly that extraordinary claims require extraordinary evidence. They argue that we haven't exhausted natural explanations. They insist that jumping to alien technology is premature, unscientific, irresponsible. But here's what those critics aren't addressing: the data itself. The brightness patterns, the velocity correlations, the predictive lead times. These observations exist. They're reproducible, they're statistically significant, and nobody, not one mainstream researcher, has published a comprehensive natural explanation that accounts for all of them. Instead, we get silence, deflection, vague promises of ongoing analysis that never materialize, and when independent researchers try to fill that gap, their work disappears from servers, their papers go unreviewed, their careers stall. Why? Perhaps because the implications are too destabilizing. If 3i Atlas is artificial, even partially, it means intelligence exists elsewhere in the galaxy. It means that intelligence has achieved interstellar travel, even if only in the form of unmanned probes. It means we're not alone. And it means we've been under observation, perhaps for a very long time. That's a lot for society to process. Governments, militaries, religious institutions all have vested interests in maintaining certain narratives about humanity's place in the cosmos. An interstellar artifact passing through our solar system, broadcasting its presence through observable brightness patterns, would shatter those narratives. So maybe the silence isn't scientific caution, maybe it's institutional self-preservation, maybe it's fear. Let's consider the timing. 3i Atlas entered our solar system sometime around 2020. It drifted unnoticed for years, too distant and too faint to attract attention. Then in July 2025, as it approached Jupiter's orbit and began to brighten, it was discovered. By October, it passed perihelion, its closest approach to the Sun, at a distance of about 0.23 astronomical units. And now, in November and December, it's moving outward again, still visible from Earth, still flickering with those inexplicable brightness patterns. What happens next depends on us, on whether we have the courage to look honestly at what we're seeing, on whether we prioritize truth over comfort, knowledge over control, because 3i Atlas isn't the last interstellar object that will pass through our system. We've detected 3 so far: Oumuamua in 2017, 2i Borisov in 2019, and now 3i Atlas. But estimates suggest dozens, perhaps hundreds, pass through undetected every year. Most are too faint, too fast, or in the wrong part of the sky for our surveys to catch them. What if some of those objects are like 3i Atlas? What if they're carrying information, technology, perhaps even warnings? What if the galaxy is crisscrossed with these travelers, left by civilizations that rose and fell millions of years ago, still functioning, still broadcasting, waiting for someone to notice? We're noticing now. The amateur astronomers, the independent researchers, the few brave professionals willing to risk their reputations, they're all watching, they're all documenting, and the patterns are becoming clearer. Webb and his team have identified what they call burst sequences in the brightness data. These are clusters of rapid flickers lasting 10 to 30 seconds that occur at seemingly random intervals. But when they plotted the timing of these bursts against 3i Atlas's position in its orbit, a pattern emerged. The bursts occur more frequently when the object is aligned with certain directions in space. Specifically, they increase when the comet's trajectory points toward the galactic center. Is that meaningful? Maybe, maybe not. But it's another data point that doesn't fit random chance. Another piece of the puzzle that suggests organization, purpose, design. And then there's the 18-hour pulse, that slow, regular cycle underlying the faster fluctuations. Webb's team tried to match it to possible rotation periods, but 3i Atlas's rotation, if it's rotating normally, should be much faster, probably measured in hours, not 18 hours. So what's causing that rhythm? One researcher who asked not to be named suggested it might be a power cycle. If there are active systems inside 3i Atlas, they might operate on-duty cycles to conserve energy. 18 hours on, some period off, maintaining themselves over the vast spans of interstellar travel. It's speculative, it's unfalsifiable with current data, but it fits the observations better than anything else. We need better data. We need a mission to 3i Atlas, a spacecraft that can approach it, image it at high resolution, analyze its composition directly, perhaps even land on it. We have the technology. We could launch such a mission. It would take years to reach the object as it speeds away from the sun, but it's still possible. The window is closing, but it hasn't closed yet. Will we do it? Will any space agency commit the resources, accept the political risk, pursue the question seriously? Or will we let 3i Atlas slip away, back into the darkness between stars, carrying its secrets with it? History will judge us by how we answer that question, because this is one of those moments when our civilization stands at a threshold. We can choose to investigate, to seek truth, regardless of where it leads. Or we can choose comfort, the familiar narratives, the pretense that we understand everything and that nothing truly strange ever happens. But the brightness patterns don't lie. They're there in the data, night after night, clear and undeniable. Something inside 3i Atlas is responding to its journey through our solar system. Something is active, reactive, possibly intelligent, and we're running out of time to find out what it is. The amateur observers will keep watching. They'll keep recording, keep measuring, keep publishing their findings on whatever platforms will host them, because they understand something that institutional science has forgotten. Discovery doesn't respect authority, truth doesn't require permission, and the universe doesn't care about our comfort or our careers. 3i Atlas came from somewhere we cannot see, survived conditions we can barely imagine, and arrived here exhibiting behavior we cannot explain. It's showing us something, telling us something, broadcasting perhaps a message we're only beginning to decode. The question isn't whether the patterns are real. They are. The data proves it. The question is whether we have the wisdom to acknowledge what they mean, whether we're ready to accept that the cosmos might be far stranger, far more populated, far more alive than our textbooks suggest. Because if 3i Atlas isn't rotating normally, if its brightness reveals internal structure and responsive systems, then everything changes. Our understanding of interstellar objects, our place in the galaxy, our assumptions about intelligence and technology, and the likelihood of contact, all of it shifts. The brightness patterns are showing us the way. They're revealing structure where we expected chaos, purpose where we expected randomness, intelligence where we expected nothing but ice and rock. 3i Atlas isn't rotating normally. It's doing something else, something we don't have words for yet, something that should terrify us and inspire us in equal measure. Because if we're seeing what the data suggests we're seeing, then we're not alone. We've never been alone. And the visitors, the travelers, the ancient probes and artifacts, they've been passing through all along, waiting for us to develop the technology to notice, waiting for us to ask the right questions. And now we're asking. The amateurs, the independents, the few brave professionals. We're watching 3i Atlas as it moves away from us, still flickering, still pulsing with those impossible patterns, still broadcasting whatever message it carries, still performing whatever function it was designed to perform millions or billions of years ago by minds we cannot begin to comprehend. The brightness patterns that reveal internal structure, the irregularities that suggest purpose, the correlations that point toward intelligence, they're all there in the data, waiting for anyone brave enough to look. 3i Atlas isn't rotating normally, and nothing will ever be the same.